example for Potier method. So the discussion of the Potier method is posted in your MVLE. So example number 1, a 3-phase 6000 volts alternator has the following open circuit curve at normal speed. So we have field amperes 14, 18, 23, 30, and 43. The 3-phase terminal voltage are 4,000, 5,000, 6, 7, and 8,000. With the armature short-circuited and full load current flowing, the field current is 17 amperes, and when the machine is supplying full load of 2000 kVA at zero power factor, the field current is 42.5 amperes and the terminal voltage is 6000 volts. So this 6000 volts is in 3-phase. Determine the field current required when the machine is supplying the full load at 0.8 power factor lagging. So what we do here first is we will get the single phase of this terminal voltage because they are in 3-phase. So we will have a single phase analysis. Here we have the field ampere is 14, 18, 23, 30, and 43. Terminal volts per phase 2,310, 2,887, 3,465, 4,042, and 4,619. At zero power factor, we have field current which is 42.5. The zero power factor, the field current is 42.5 amperes. At this voltage 6,000 and its single phase is 3,465. So you will just divide this one by square root of 3. At short circuit, the field current will be 17 amperes. So with armature short circuited, full load current flowing, the field current is 17 amperes. Now we will draw the OCC and the ZPFC, the open circuit curve and the zero power factor curve. First one, point OA is our 17 amperes, which is the field current at short circuit. So from 0 to 17, that is your point OA. And then for us to draw the ZPFC, you will locate your point B. So point B is the 42.5 amperes, which is the zero power factor field current. And then you will connect the 17 amperes and your point B. Now you will have your ZPFC. Next is your OCC. You just draw the curve corresponding to field current and terminal voltage. So for point field current, which is the x-axis, 14, you will have a terminal voltage equal to 2,310. So approximately this is 14, and then this is 2,310 until 43, this one, 43, and then its corresponding terminal voltage is 4,690. Then connect all the points, you will have your OCC. After that, you will draw a tangent line with respect to OCC. That is your air gap line. Measure point DH. So this one, the point CB, C and B is equal to point OA. So all of this discussion is posted first in your MVLE. The length of OA is the same as the length of CB. Okay? And then measure the DH So DH, how will we draw this triangle? Draw a tangent line. After we draw the tangent line, which is the air gap line, we'll have a parallel. This one, point CD is in parallel with our air gap line. So you will connect point C and D with respect to air gap line. So parallel yung air gap line and then point CD. After connecting this CD, you will just connect point DB. And then draw a perpendicular line between D and H. This one. So this is a perpendicular. After drawing this triangle, you will measure the point DH. So measure DH, this is approximately 450. Our DH is the drop in your XL. So that is IAXL. Point DH is reactance drop, IAXL. Now we can solve your E. So this is the general formula for E, but since IARA, the drop in armature resistance is not given, so that is equal to 0. Only the IAXL. So E is equal to the terminal voltage plus IAXL vectorially. The formula is E is equal to square root of V cosine phi squared. Our phi here is the power factor. Plus B sine phi plus IXL squared. So V is equal to this one. The single phase of 6,000. That is 3,465. So square root of 3,465 times the power factor, which is 0.8 squared, plus 3,465 times the sine function of 0.8. So cosine theta is equal to 0.8. Theta is equal to 36.87. And the sine function of sine of 36.87 is equal to 0.6. So this is just square root of V cosine phi or theta squared plus V sine theta plus IAXL squared. That is equal to 3,752.31 volts. So reflect this voltage in or to OCC, then get the corresponding field current. 3,752. This is our OCC, and then you will get the corresponding IF, which is 26.5. So IF at E is equal to 26.5 amperes. Next, measure the point BH. This one, point BH here in our IF x-axis. So if you will measure this one, you will get approximately 12.5 amperes. So that is 42.5, and H is approximately at 30. So 42.5 minus 30 is 12.5. So after getting the field current at E and the field current BH, you will have your triangle similarly in the previous methods. So this is our 26.5. And this will be the 12.5. 90 degrees for lagging power factor. So, nandito yung 12.5. And this angle is our power factor. So, for us to get the total field current, we will add this one vectorially. Using cosine law, you will get IFT is equal to square root of 26.5 squared plus 12.5 squared minus 2 times 26.5 times 12.5 cosine of The total angle of this is 90 plus 36.87. So IFT now will be equal to 35.44 amperes. Example number 2. An 11 kilovolt 1000 kVA 3-phase Y-connected alternator has a resistance of 2 ohm per phase. The open circuit and full load zero power factor characteristics are given. This one. Find the voltage regulation of the alternator for full load current at 0.8 power factor lagging by Potier method. So these are the open circuit and the zero power factor characteristic, and also the field current. This OCC line voltage and line volts, zero power factor, of course, they are in line to line. So we will get the per phase values of this one, and then we will plot against the field current. For field current 40, 50, 110, 140, and 180, their OCC per phase will be 3000. This is the open circuit characteristic, OCC. 3,349. That is 5,800 divided by square root of 3. Until 15,000 divided by square root of 3, that is 8,660 volts. Also, the per phase volt zero power factor is divided by square root of 3. For 1,500 divided by square root of 3, that is 866. Until 12,500 divided by square root of 3 is 7,217. So if we are going to plot the field current, which is the x-axis, and the OCC per phase and per phase volt zero power factor is our y-axis, we will end up this curve. So the first curve will be the OCC, and the second curve will be your ZPFC, or the zero power factor curve. First, we will solve the full load current. Given that our apparent power is 1000 kVA, full load current will be equal to square root S divided by square root of 3 multiplied by the line voltage, which is 11,000 volts. So that is 1000 times 10 raised to 3 divided by square root of 3 times 11 equal to 52.5 amperes. And then, after natin makuha yung full load current, we need also to convert or to solve the per phase value of this 11,000 volts. For 11,000 volts, that is 6,350 volts. Now, after we draw the OCC and ZPFC, the air gap line will be in parallel with respect to the OCC, or I mean tangent with respect to the OCC. This will be our point OA as discussed in the previous videos. This is the point OA, and the length of this point OA is the same as the length of BC. Okay, OA is equal to BC. Now, we will reflect the 6,350 in the zero power factor curve. This will be now your point B. So, approximately this is 6,350 at point B. And then, the length of point B to C is equal to the length of point A to O, or OA. Now, point DB, this one D and B, is the drop in resistance, that is IRA. The I is the full load current, which we solved earlier, that is 52.5 multiplied by the per phase armature resistance, which is 2. The IR drop will be 105 volts. Next, point DH, this is H, is the drop in leakage reactance, or the IXL. You can measure this one in your x-axis. So approximately that is 1,000, in y-axis. Point DH, this one, D and H, ito pala. So i-reflect nyo lang tong H dito, and then you will get approximately 1,000 volts. Solving now your E, that is equal to the square root of V cosine theta or phi plus the drop in IRA squared plus V sine phi or theta, that is your power factor, plus IXL squared. So V, 6,350 times the power factor is 0.8 plus the drop in IRA, which is 105 squared, plus 6,350 times sine of the power factor, that is 0.6, plus 1,000 squared. So you will get 7,080 volts of E. Now we will reflect this value in our OCC, then get the field current. This is approximately here, 7,080. Then i-reflect nyo sa field current and you will get approximately 108 amperes. So that will be your IF1, 108 amperes. Measure point BH. Ito, point B and H. That will give you the value of your field current 2. So 140 minus that is 110 equal to 30 amperes. After getting IF1 and IF2, you are now going to solve for IFT. This is your IF1 and this will be your IF2, 90 degrees, and then this is your power factor. Vectorially, add them vectorially and you will get IFT, or using the cosine law, IFT now will be square root of 108 squared plus 30 squared plus 2 times 108 times 30 cosine of 90 plus 36.87 equal to 93.14 amperes. Then reflect this IFT again to 2 OCC para makuha yung no load voltage, which is your EO. If we are going to reflect that one, you will get 7,000 volts. Solving now your percent voltage regulation. From our formula, EO minus V divided by V times 100 equal to 7,000 minus 6,350 divided by 6,350 times 100 equal to 10.23%.